Welcome back, everybody. It's been a little while. This is Lecture 16, Part 1, an introduction to atomic structure and the history of the atom, the discoveries that have contributed to our current understanding of the structure and properties and nature of atoms. We are now in Chapter 5 of our book. It's taken us some time to get out of Chapter 4, and I'm looking at page 259 of the textbook or 267 of the ebook. A closer look at matter, Chapter 5. We can see here on this page that there's a model of an atom, and that's a fairly commonly depicted model of an atom with at the center the nucleus containing protons and neutrons. We'll talk about their charges. And these rings, these energy levels, this is a Bohr model, by the way, suggesting that these electrons exist in these rings or energy levels, or shells you might call them, outside of the nucleus. I want to remind everybody that the models of the atoms that we draw are a gross misrepresentation of reality. Atoms are unimaginably small, and the nucleus of the atom is significantly smaller than this size of the atom itself. There's a common analogy we use that says that if an atom were the size of a large stadium, there'd be a golf ball in the middle. There'd be a golf ball in the middle, that would be the nucleus, and a few grains of rice out in the stands, and everything else would be empty space. An atom is overwhelmingly empty space, much like if all there were in a stadium were a golf ball and a few grains of rice, there'd be a lot of empty space as well. So I'm going to start you off with a Bozeman science video, a crash course video on the history of the atom. It's 9 minutes long. If you are not interested in learning about the history of the atom, that's your choice. You could skip ahead to when you no longer see him and you see me again. If, on the other hand, you want to read about the history of the atom from your book, you could read pages 260 to 265. So you could either watch this segment from Crash Course, read from your book, or skip the history of the atom section altogether and fast forward to when you see me once again show up on your screen. Never mind that. I'd planned to embed the video within this video, but then I had my mic on and there was reverb and it didn't come out so well. So instead, go to YouTube, please. Put into the search bar, History of the Atom Crash Course. Click on this, History of the Atomic Chemistry Crash 37. Watch that video if you so choose, and then come back to this main video when you're done. All right, welcome back. So hopefully you enjoyed that story about the history of the discovery of the atom. It's not crucial that all made sense, but I find it really interesting to know what it took for us to, in the year 2020, know what we do about the atom today. So I take you now to page 273 of the ebook, or 265 of your textbook, where we're looking at this table at the bottom of that page, which is the composition of the atom, table 5.1.2. This is reminding us that there's three basic subatomic particles in an atom, or there are three subatomic particles in an atom: protons, neutrons, and electrons. A common abbreviation for a proton is P with a little plus. For a neutron, it's N with a little superscripted 0, and electron is E with a minus. And those symbols, the plus, the 0, and the minus, are telling us their relative charges. Protons have a relative charge of 1 plus. The actual charge in coulombs is very, very small, but their relative charge is 1 plus. And what their charge is relative to is the charge on an electron, which is 1 minus. Protons and electrons have the same magnitude of charge, but they have opposite charges, and their charges cancel. The relative mass of these subatomic particles in a unit called atomic mass units, which is a very, very, very small unit for mass, is 1 AMU for a proton, 1 AMU for a neutron, meaning protons and neutrons have the same mass, although neutrons actually have one electron's more mass than a proton does, because a neutron is actually a proton that has captured an electron. So we say they both have 1 AMU, and because electrons have so little mass compared to protons and neutrons, about 1/2000th the mass of either, we say they have negligible mass or no mass. Electrons do have mass, but it's so small or negligible that we don't account for the mass of electrons when we talk about the overall mass of an atom. Here are their absolute masses in grams, substantiating that the AMU unit must be really small because 1 AMU is 1.67 times 10 to the minus 24 grams. And as you may know, protons and neutrons are located inside the nucleus. Their actual composition in the nucleus will not be important for us in this class. That's more about nuclear chemistry. But the location and the properties of the electrons outside the nucleus is what we're going to talk at length about, first through the Bohr model, and then we'll get into the quantum model and look at how these electrons actually exist in these probability states in orbitals. So we've flipped the page. We're now on 266 of our textbook, or 274 of our ebook, looking at the section titled Atomic Number, Mass Number, and Neutron Number. Looking at this section that's highlighted in yellow here, which says that the mass number, abbreviated capital letter A, for each atom equals the sum of the protons and the neutrons in the nucleus. A proton and a neutron, which we already know, have the same mass of 1 AMU. Each contribute 1 unit to an atom's mass number. And again, although electrons do have mass, it's so negligible we don't account for the mass of electrons in the overall mass of an atom. So if we add up the number of protons to the number of neutrons, we get the mass number, abbreviated once again a letter A. And the mass number of an atom, or the mass of an individual atom, is going to be in atomic mass units, because that's the unit for the mass of a proton or a neutron. As we go down to this little section in green, this is the Azx notation that may be familiar to you from Chem A. X represents the element's symbol. So if we go down below, we see an example of that. X down here is N for nitrogen. The atomic number Z is written in the lower left-hand corner, and for nitrogen that's 7. I'd like to remind you the atomic number, which defines that element or that atom, is the number of protons in the nucleus, and then above it, abbreviated the letter A, is the mass number. And for nitrogen, in this case, that's 14. If this nitrogen atom weighs 14 and it has 7 protons, then we would know it has 7 neutrons also, because 14, the sum of the protons and neutrons, minus 7, the number of protons, gives us 7 neutrons. Here's a fluorine atom with an atomic number of 9. It has a mass number of 19 and has 10 neutrons, because 19 minus 9 is 10. So we flipped our page. We're now on 267 of our textbook, and we're going to talk about ions. Ions, and I'm reading the bit in yellow here, are an electrically charged atom. Atoms can be charged, and they're called ions, or groups of atoms. Polyatomic ions are groups of atoms that collectively have a charge. Charges are obtained by atoms, or groups of atoms, through the gain or loss of electrons. It's only electrons that can be gained or lost by atoms, not protons. Protons are always locked into the nucleus. In green it says for every electron an atom gains, it also gains that amount of excess negative charge and becomes a negative anion. Negative ions are called anions, the prefix an meaning negative or without. If an atom gains 2 electrons, it will gain a 2 negative or a 2 minus charge. If an atom loses 2 electrons, it would become a 2 plus ion or have a 2 plus charge. Each electron lost by an atom leaves that amount of excess positive charge, or results in that great a loss of negative charge, forming a positive ion or a cation. Again, negative ions are called anions, and positive ions are called cations. Down below, we've got the Azx notation for magnesium. Magnesium has an atomic number of 12, lower left-hand corner, a mass number of 24, and in this case, it's got a 2 plus charge, meaning it's lost 2 electrons. And if you recollect that all atoms are neutral unless we know otherwise, neutral magnesium would have 12 electrons because it has 12 protons, but because it has lost 2 electrons, it has a 2 plus charge, it has only 10. Here's phosphorus with a weird Azx notation. That 15 should actually be in the lower left, so it has 15 protons, it has a mass of 31, so we know it has 16 neutrons, and with a 3 minus charge, it's an anion, which means it's gained 3 extra electrons. If it were neutral, it would have 15. Having gained 3, it has 18 electrons. So there are the Azx notations for 2 ions, magnesium and phosphorus. So I've scrolled down a bit. We're on the same page, and we're going to solve a few of these practice problems together here on page 267 of your textbook. I'll take you to the whiteboard where I can write more easily than I can in this digital book. So I'm going to do 1A and 1B with you, but I recommend you maybe try those on your own first and pause the video and then come back when you're done and see how your solutions compare to mine. Try 1A and 1B on your own first. All right, so remember that the atomic number is down here. It's in the lower left-hand corner. That's the number of protons. So P plus equals 20. That number in the upper left-hand corner, the mass number, abbreviated A, is the sum of the protons and the neutrons. Because we know there's 20 protons, 40 minus 20 is 20, so we've got 20 neutrons. And if this calcium atom were neutral, it would have an equal number of electrons and protons, meaning 20 electrons, but because it has a 2 plus charge, that means it has lost 2 electrons, or it has 2 more protons than electrons, so electrons is going to equal 18. All right, as I go over to tellurium, atomic number is 52, so protons are 52. Uh-oh, that's 25, not 52. Protons are 52. Neutrons will be the mass number, 128, minus the atomic number, 52. So in my head, that's 76. I think I've got that right. And then electrons, if it were neutral, would be 52, but because it's an anion, because it's negative, it has gained electrons. It has gained 2 from 52, so it has 54 electrons. I'm going to skip 2, because all we'd be doing is writing the symbol and the atomic number in the lower left. We aren't given the number of neutrons. We wouldn't know the mass number, so we'll skip 2. I don't see a lot of value in it. But let's do a couple rows down here. This should look familiar from some of the stuff you did back in the day in Chem A. I'll do this third row here where we're given information about the atom. We need to make the Azx notation out of it. So we got an atomic number of 47. So we know that 47 is going to go in the lower left-hand corner. In a moment, we'll have to go to a periodic table to figure out what atom this is. Mass number of 109, so that goes in the upper left-hand corner, 109. And again, we've got to figure out what the symbol is here in just a moment. If it's got 46 electrons and 47 protons, we know that there's one more proton than electron. We know it's positively charged. Should put the 47 protons in there. And therefore, I'm going to put a 1 plus charge in the upper right-hand corner. Again, we still need to put the symbol in there. And the number of neutrons is going to be the mass number minus the atomic number. 109 minus 47 is 53 plus 9, 62 neutrons, if I did my math right. I think I did. So I'm going to take you to the internet for a periodic table so we can find element 47. Here we go. So here's a periodic table. I want to remind everybody that on the periodic table, the atomic numbers are usually above the symbols, whereas in the Azx notation, the atomic number is always in the lower left. The periodic table, it's usually, again, above the symbol. So we're finding 47 here. It looks like that's silver, so we need to put into the Azx notation the symbol for silver. So there we go. There's silver. And we're looking good. All right, let's do the top row real quick. Let's fill in the information for molybdenum. The atomic number, which is in the lower left, is 42. The mass number, oops, I can't see now, in the upper right is 95. Number of protons is always the atomic number, 42 again. Neutrons is going to be mass number minus atomic number. 95 minus 42 is 53. And because there's nothing written there in the upper right-hand corner, we assume that it's neutral, which is a reasonable assumption. And if it's neutral, the number of protons equals the number of electrons. So we're looking at 42 electrons for a neutral atom of molybdenum. So the last part of this lecture will be about isotopes. Isotopes are different versions of the same atom that have the same number of protons but a different number of neutrons. Isotopes are atoms of the same element, or atoms that have the same number of protons but a different number of neutrons. And that's what it says up here in yellow. And because they have a different number of neutrons, isotopes will have a different mass number from each other. We only really care about isotopes, at least in this context of this class, in terms of the contribution they make to the average atomic mass of the atom, that decimal number that we've been using off the periodic table to find molar masses from. In blue, the book tells us, or reminds us, that it's really the number of protons, but more specifically the number of electrons that atom has, and how many electrons that atom has, and what energy level they're in that dictates or determines the properties of that atom. It's not the number of neutrons. So different isotopes of the same element don't have different chemical properties. They just have slightly different masses and contribute, again, to the average mass of that element, the average atomic mass. It is the mass spectrometer, which I'll talk about in a moment, this device that looks sort of like J.J. Thomson's cathode ray tube, that is used to figure out what the isotopes are for an element and what their percent abundance is. What percentage of the atoms of a particular element are each isotope. And I'll explain how a mass spectrometer works, at least in a real basic sense here right now. So here's an image, a basic image of a mass spectrometer, which again looks a bit like a cathode ray tube. Let's pretend that a pure sample of zirconium, the element zirconium, is loaded into this mass spectrometer. And the sample enters the mass spectrometer here. This is pure solid zirconium. It's a metal. And zirconium has several different isotopes. Zirconium has several different versions of that atom that have the same number of protons but a different number of neutrons. So the sample is loaded into the mass spec, and then a beam of electrons is shot at that sample as it's being heated so that the solid atoms become gaseous and are free to move. And the beam of electrons has stripped some of the electrons off the zirconium to make them positively charged. So these are ions. These are ions that are now traveling through this mass spec, or this cathode ray tube. Those particles are then accelerated. Don't worry about how, but they're accelerated, so they're now traveling very quickly through this tube. And they then travel through the tube and through a magnetic field. What that magnetic field does is alters the motion of, or deflects, the beam of positively charged atoms. And the more massive atoms, because they are more massive and have more momentum, deflect less. The more massive atoms are deflected less than the less massive atoms. So we'd see the more massive atoms up here and the less massive atoms down here. It's a very sensitive device. The degree of deflection can be measured, and an algorithm is applied where mathematically the mass of the isotopes can be determined based on the degree of deflection. The detector also detects not how much they were deflected, but how many of those particular atoms hit the detector. So it's telling us how many atoms hit the detector, and based on how they deflect, how far they deflect, what their mass is. And what gets spit out is this graph, which tells us the masses of the different isotopes, which is based on the degree of deflection. The zirconium 90s would have been deflected most because they're the least massive, and the zirconium 96s would have been deflected the least because they're the most massive. And the height of these peaks represents how many of those particular ions hit the deflector, or what their relative abundance is. So what this graph is telling us is that zirconium has 1, 2, 3, 4, 5 isotopes that weigh 90, 91, 92, 94, and 96, and that have a percent abundance of 51, let's say, 10 or 11, 17 or 18, and so on and so forth. Then, those data, the masses of each isotope, and their percent abundance can be used, and I'll show you how to do this, to calculate the average mass of zirconium. Some zirconiums weigh 90, some weigh 96, others weigh in between. The average mass of zirconium is based on the mass of these isotopes and their percent abundance. So we're back to our book, back to the page we were on, 268 of our textbook, 276 of our ebook. And we're looking at the sample problem here. It says to use mass spectrometry data below to calculate the atomic mass of neon. And if we were to see this in a graph, we'd see 3 peaks, one at 20, one at 21, one at 22 on the x-axis. And then the heights of these peaks would be their percent abundances. The neon 20 peak would be by far the highest at 90%, neon 21 at 0.27, and neon 22 at 9.25. The average mass should be somewhere between 20 and 22, and it should be closest to 20 because this is what's called a weighted average. With a greater abundance of neon 20, the average neon atom is going to weigh closer to 20 than 21. So our book tells us that a weighted average is essentially a sum of the masses of each isotope multiplied by their percent abundance. It's the mass of each isotope multiplied by its percent abundance added together. So how that looks when we solve it is we take the mass of neon 20, and if we didn't know what the actual mass of neon 20 was, and don't worry that it's not quite 20. There's a reason why, don't worry about it. If we didn't know what the actual mass was, we would just take 20 times 90.48%, or 20 times 0.948. But because we do know the actual mass, we can see that down here we're taking 19.9224 AMUs and multiplying it by 90.48 as a percentage, which is 90.48 divided by 100, or 0.9048. So it's the atomic mass, it's the mass of the atom times the percent abundance plus the atomic mass of the second isotope times its percent abundance times the mass of the third isotope multiplied by its percent abundance, and that works out to the average atomic mass, or the weighted average, which is 20.18 AMUs. So we've flipped our page, we're on 269 of the textbook, or 277 of the ebook, and we're going to do practice problem 1 here. I recommend you trying this one on your own, and then come back after you pause the video and check to see how your solution compares to mine. All right, I've written up the formula here that reminds us the atomic mass, or the average atomic mass, is the percentage of isotope 1 times the mass of isotope 1 plus the percent of isotope 2 times the mass of 2, and if there were a third, it would go on, but there's only 2 isotopes here. In this case, it's going to be 60.11%. I just convert that to a percentage in my head by sliding the decimal 2 to the left, so 0.6011 times the mass, which is 68.9256, plus the percent of isotope 2, 0.3989, times its mass, which is 70.9247. So I go to my calculator, and I got 68.72304,099, but because the percent abundances had only 4 sig figs, my answer should as well, so I'm going to end up with 69.72. 69.72, and the unit is AMU. So we're still on that same page, but I've scrolled up a bit to the sample problem at the top of page 269. And this is essentially backward of what we just did. In this problem, it's telling us that boron has 2 naturally occurring isotopes, and to calculate the percent abundance of boron 10 and boron 11 using the following data. In this case, we know what the atomic mass is, and we know what the mass of each isotope is, we just don't know their percent abundances. This isn't a real realistic thing in chemistry to do, it's just a fun way to do more math. So we apply the same formula, which is the percent abundance of an isotope times its mass. So here's the percent abundance of boron 10, which we don't know. We're setting it equal to x. We don't know it, so it's a variable. So the percentage times its mass plus the percentage of the other isotope times its mass equals the average mass. If we say that boron 10's percentage is x, and we know if there's only 2 isotopes that they add up to 100, but percentages really add up to 1, then if one of the percentages is x, the other one is 1 minus x. So we've got just one variable, x, in here, and through algebra, we isolate x and find that x is 0.2, which you know mathematically is 20%. So boron 10's abundance is 20% because it came out to 0.2, and if we know that the other one must be what it takes to get to 100%, it's 80%, 100 minus 20 being 80. So this can also be solved backward, where we're given the atomic mass, we're given the masses of each isotope, and we can find their percent abundances if we want to, when we're wanting a little bit of joy in our lives. That's it, folks. I'll see you soon for Lecture 16, Part 2, the Bohr model of the atom and emission spectroscopy. Have a great rest of your day. Be kind to your neighbors, love yourself. Peace out.